operations. So this is important. The architecture is a lot larger than that, right? Remember, we looked at the block diagram of the LC3 and we've seen the program counter. The program counter is very vital, but you cannot get to the program counter directly. If you want to modify the program counter, you just can't write to the program counter. You can't write to it directly. You have to use a jump or a branch instruction that writes to the program counter indirectly. And then also memory organization is important. You need to understand this. So anytime you program at this architecture, you need to know what's visible to the programmer. You need to know how many locations can be addressed. Let me give you an example. An 80, 86, 186, 286. Even though the 286 it was capable of addressing a large memory location, at any one time you only had 20 bits of address that you could address, which was 1 megabyte. So if you needed to address larger, if you had 8 megabytes of memory. I'm talking about megabytes. You guys are used to gigabytes, right? It only addressed 1 million bytes. You had to change the address registers so that it pointed to different parts of memory. So you need to know how many bits per location. This is the addressability, address space. Register set, how many, what size. Register size is like I showed you on a Pentium, is 8-bit, 16-bit, 32-bit. LC3 is 16-bit, they're all 16-bit. How are they used? Now the other thing too, this is important on how they're used, because most processors do not have, well they call them general purpose registers, but they're not. For in a Pentium, you can abstract, multiply, divide in AX, but if you want to increment anything, you got to use CX and DX. You can't increment in AX and BX. And so they're not general purpose.
What is CX and BX and AX and all those other X's?
Those are just name of registers,
Okay.
register names. LC3 calls them R0, R1, R2. Pentium calls them A, B, C, and D.
That's just my question.
Yeah, that's all. So this is important. So you need to know these things before you can program at an ISA level. You need to know the opcodes. Typical processors now, CISC processors usually have 200 instructions. That's about what a Pentium has, a couple hundred instructions. LC3 would be considered a RISC processor. That's a reduced instruction set. It has only 16. PDP-8, we had 8. The data types. In the LC3, we have, how many data types do we have in the LC3?
One.
What is it?
Binary.
Two's complement,
Yeah, just come.
integer. That's the only data type this has. Other processors would have other data types. Pentium has, you guys know how many data types? Byte, word, double word, and those are all ints. And it also has floating point. There's a floating point ALU in a Pentium. So a Pentium can handle floating point numbers directly. So those are not abstract data types. They're data types. And then addressing modes. And what addressing modes is how do I get data into my register set. Direct address, in other words, I give it an address. Indirect address is what? What's indirect addressing? you guys that's had C++.
Stored in memory.
Well, it's a pointer to a pointer.
Yeah.
So you either point to memory or you point to a pointer that has memory, that points to memory, so double indirection. So you have all these different addressing modes, and each ISA can be a little bit different. Any questions on that? You need to know these things to program. So in other words, we need to know this, and these things before we can program it. So that's what we want to look at today. Okay, let's look at the memory. To the 16th locations, we have 16 address bits. So that's how big? To the 16th. 16 bits.
65,000.
65,000, yeah. Okay, so you know, in computers, you ought to really know the powers of 2. Right? Anybody name them? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 163, 60 something, 32 something, couldn't remember. 65 something, 120.
8.
I used to know to the 22nd, but I'm old now and I can't
2 to the
remember.
22nd.
Yeah, to the 22nd.
Is 2 to the 16th good enough?
Oh, yeah. I'd say now, if I was going to school, I'd know 2 to the 32nd, because that's how big the processors are. I can't remember anymore, but you know what, I can look them up, or I can calculate. Okay, registers, temporary memory, you gotta remember that, we have R0 to R7, that's their mnemonic name, so that's what we'll call them, and they're each 16-bit wide. So they're not variable length, they're fixed length. So the question is, how many bits to uniquely identify a register? How many bits?
4?
No?
16.
We did an example already.
16.
No,
3.
3.
Which?
Because it's 8.
3 bits has 8 combinations. So with 3 bits, I can identify any register. You remember what we just did in the book? What page was it?
123.
Remember, I can identify that as register R1 because of these 3 bits. Right, there's 8 combinations. So I can, 000 is R0, 111 is R7, and everything in between. So here's R2. So I can uniquely identify the registers in 3 bits. So that's its address. It's only a 3-bit address. So we know uniquely address memory is 16 bits, uniquely address registers is 3 bits. Other registers, not directly addressable, but can be used by affecting instructions. Those are what kind of registers? Remember I told you the program counter? You cannot write to the program counter directly. You have to execute an instruction that will affect the program counter, like jump. And then you have another register that you cannot read or write directly, but it affects, and I haven't talked about this yet in this class, but condition codes. Does everybody know what a condition code is?
No.
Let's talk about a condition code.
Unary.
Well, I read about it in the reading.
Negative, positive,
about,
0.
You know, the positive, negative, 0.
Uh-huh.
But in the reading, it made it sound like there were set parameters for each one of those codes, and I didn't understand where they were getting.
Okay, let's just look at this, because this is really important. Because the only, in any ISA, the only decisions you can make are decisions about the condition codes. In a Pentium, in a 68,000, a Power PC, any of those, the only decisions you can make are decisions on the condition codes, and that's it. So anytime you wanna make a decision, that's the only thing you can make decisions. You can't make decisions on anything else, but just a condition code. This condition exists, I wanna do that. So when you guys write your programs, and in your programs, you have to make decisions, you have to make decisions on your condition codes. So you wanna do some kind of operation that will set the condition codes that you have that are important so that you can make a proper decision. Now in the LC3, there's 3 condition codes. Negative, positive, and 0. And these condition codes are set when you write to a register. Anytime you store information, that sets the condition codes. That is the only time that sets the condition codes. And so you gotta remember, you gotta store something to set your condition codes. And whatever it stores, it will look and say, if that register is all zeros, it will set that code. If that register is greater than 0, it'll set this code, and if that, and what do they use for negative?
When the code for Z is 1? 0, right?
Think about it,
0.
When there's a one in there,
when there's a 1,
in that
A
negative
negative
position.
one.
In
yeah,
bit.
well, where's the negative bit?
First bit.
What's that?
The most significant.
Yeah, R15. Or, I'm sorry, B15, right? When B15 is equal to 1, this bit's set, right? Because the only natural data that we have is 2's complement. So when bit 15 set, that bit's set. Now these bits are mutually exclusive, meaning what?
There can be only one.
Only one set. So you only have one condition code set. Now you can test for as many as you want, but only one, the number is only 0, positive, or negative.
Can't you have an 80 0?
No. No, see,
It's 2's complement.
negative 0, so a negative with all zeros is what?
0.
No, it's the smallest number you can have, right? Which is what in the LC3? Minus 16,331.
31?
Minus 16,000, right? Everybody agree with me? Yeah, it is. Okay, op codes, there's 15. I won't be going over this, but hopefully Dr. Olson will. 15 op codes. We have 3 operating instructions: add, and not. We can do all with add. You know how to subtract with add, right?
Mm-hmm.
How do you do an or? You can. You guys did it in an assignment already.
We did.
And a not.
You did it with a not, with an and gate, right? And a not's an and.
And a not is a not. An and, right? Is that what you're saying?
You,
So if I wanna do an or, how do I do an or?
it's a not with a
So I can take
parentheses and-
registers, I wanna say, or, register 0 or register 1 and store it in register 2, how would I do that?
You do, not register 0.
Register 0 not,
And,
what's the next thing you do?
and,
No,
not,
not, register 1,
and then you add them, isn't it?
then you and, register 0 and register 1. put that into register 2. Are we done?
And
Yeah.
not that.
Then you not register 2 and put it into register 2. So to do that,
Is it Moore's law or
we
something?
have to have an algorithm to do that, right? But we can OR. And we can NAND, so with these things here, with add we can add, subtract, multiply, and divide. And with and not, we can do all combinations, because you guys did that as an assignment already. I can make NOR gates, AND gates, NAND gates, not gate, nots. Okay?
When will we get those assignments back?
As soon as Dr. Olson corrects it, or whoever he has corrected. Okay? Here's data movement instructions. We have 3 loads. Load indirect, load from register. This is a special load. This is called load effective address. This is for addressing. Then we have store register, store indirect. So here's our stores. Here's our controls. These are the ones that, control instructions, what do?
Check those and PC.
Change the PC. This is how you make your decisions. Is it, the only decision you can make, the only way you can do things different in any ISA is change the program counter. Execute somewhere else. And that's it. So here's our branch. These are our jump subroutines, our jump, return, from interrupt, and trap. So these change the program counters. Then some opcodes set clear condition codes, and I told you what those opcodes are. Anything that stores memory. So does load move memory, store move memory, does add move memory?
No.
Add stores, right?
Okay.
Because I can say this, add R3, comma, R3, comma, R2. It adds R3 and R2 and stores it in R3. So that'll set a condition code. Anytime I store, I can set it, I can set a condition code. So adds, ands, and nots always set condition codes. And these is what they are. Again, negative, 0, positive is greater than 0. Data types, we talked about that, there's only one data type. Any other data type than that, you have to make a abstract data type. Okay, addressing modes, let's look at this. How is the locate, let's see, non-memory addressing, we have immediate addressing and register addressing. Okay, does everybody know what immediate addressing means?
It's within the.
In instruction.
Right, it's one of the operands, and remember it is, so in other words, an immediate address, I can't get to the whole memory, right? Because it is sub 16 bits. Because it's inside the instruction, and the instruction's only 16 bits. Okay, register, I can address as a register, so I can address all memory with that one, right? Because register's 16 bits wide. I can address, this is non-memory. So this is PC relative. In other words, I can give an offset to the program counter. I give an offset of 5 to the program counter. It'll take the PC program counter, add 5, and it'll go get that. Or I can give it a negative number, so I can offset above or below the program. So this is relative. Indirect addressing, and that's what? What's indirect?
It's a pointer.
Pointer, yeah, pointer. And then base offset. And a base would be a base register. And then I can have an offset. What would you use base offset for, guys? Think about that. You guys program at high level language, base offset. You could, but it's not called a counter. What's it called? called a index, right? This is how you make an array. You put a base address in R3, R3 equals 8,000 hex,
Oh, yeah, right.
right?
Mm-hmm.
Now if I give it an offset of 0, what's it gonna do? It's gonna go to 8,000 hex in memory. If I give an offset of 1, it's gonna go to 8001 because it'll add those together. You see how a high-level language would use this to, this is how you index arrays. Okay? Okay, in our operate instructions are and, add and not. Source and destination operations are registers. So in other words, these do not reference memory. So if you want to add, you have two locations in memory. That means you have to load this location, add them together. If you want the results in the memory, then you have to store, okay? So don't instructions, don't reference memory. Add and add can use immediate mode. What's immediate mode again?
It's a literal.
Right. You can use a number right in the instruction. Now, I can't add or add big numbers, right? Because this will be sub 16, and so there'll be a sign extension on these numbers. Okay, why don't we have not as an immediate mode? We got these two, we don't have this. Why is that?
Not as unary.
Yeah, not's a unary operator, right? These are binary operators.
Why does that matter?
Pardon me?
I don't know why that matters.
Well, immediate.
Well, if I add, I have to have two sources, because it's binary. Not, I only have one source.
So why does that make a difference? I don't understand.
Well, in an immediate mode, what that means is if I say add R3, comma, R2, comma, 5,
So you're adding 5 to R2.
I add 5 to R2 and store it in R3. Well, not is unary. I'd say not R3, comma, R3.
That makes sense.
See, I don't have to have two operands, and one of them has to be a register. One of them can be immediate or a register. See, so let's see, there's only one operand,
Okay, that makes sense.
so that's why. I just want to keep you on your toes on that one.
Yeah. What if you just want to not 5 and stick it in R3? Is there any, maybe that's a dumb question.
Yeah, if you first load it to R3 and then
How would you do that? How would you not 5 and stick it in R3?
you load to R3 and then
Or, since it's an immediate number, if it was an immediate number, I wouldn't have the doggone computer calculate it. I'd put the -5 into R3 directly. I'd just say this, add R3, comma, well, let's say R0 happens to be 0, R0, comma, -5. Or if R3 if you had R3 as 0, you could just say add R3, comma, R3, -5. Right? And then take R3, which is 0, add -5 to it, and put it in R3. In other words, that's how I'd load -5 in R3.
oh yeah.
Does that make sense?
Yeah, that makes sense.
What? So that's when you wouldn't use immediate. That was one of my questions is when do you know when to use the register or when to use immediate?
Well, okay, that's a good point. One is immediate. What do you call an immediate number in high-level language, guys?
Constant.
Yeah, constant. You know what the constant is already. It's not going to change. Okay? And the other thing is, You have to be careful on this because this constant can only be so big. It's sub 16 bits. If it's only 10 bits, that means that it has to be plus or minus 1,000. Right? If not, you're gonna have to declare a constant in memory and then go get it. So you have to load it into the register, a constant, okay? Then the other thing you have to worry about, what's this called if it's right in the instruction? Gotta be real careful with it. You guys ever talk about magic numbers? Well, that's a magic number, right? In assembly, you use a lot more magic numbers than you do high-level languages. They're actually, you can use them in high-level languages, but typically they are forbidden, right? At least in my assembly, I use these numbers, but this has to be very well documented. Very well documented. Okay, let's look at a knot. Here's an instruction, here's the knot. We have our destination and source. So the knot's real easy. We just take our source, address our source, put it in the ALU. We tell ALU to what? Perform a knot. ALU can perform three things, right? Knot,
And
add, and and. So we just say knot. Knot's unary, so I don't need anything here. Knot the ALU, and then it comes in and stores it in the destination. So that's how the ISA works. That's how instruction works. So you can see how a state machine would do that. It would take this and say, hey, I want to do a knot. It would take the source address, and it would address the register. And you can see how it would have a multiplexer come in here, bring that data into the ALU. It would say, okay, I want to knot the ALU, and then it would address the destination register with its 3 bits, and then store that into the destination register.
So it doesn't matter about B0 to B5, doesn't matter what it is? Or do they have to?
Yes, it does.
It does.
Has to be a 1. Now, you don't have to worry about this because when you use not in the assembler, you'll say not not R3, R4.
You don't have to write.
This will
anything
be, the destination will be R3, so that'll be a 0, 1, 1. This will be a 1, 0, 0. And it will fill these in for you.
else. Okay.
So you don't have to worry about that. The assembler will do that for you. Does everybody see that from the bottom? That's how simple all these instructions, you look at them at this level, they're all really, really, really simple. Okay, let's look at add and they're together because they're basically the same. The only difference is telling the ALU what to do since they're binary. So here's our add, here's our and. We have our destination, our source. Now this 0 means it's register mode.
What is register mode?
Well, add and can have an immediate mode,
Okay.
right?
Yes.
So this says, hey, this data is register data. If it's a 1, that means it's literal data. Okay, so I'll show you that on the next slide. So all you have to do is, here's your source. Take source 2, presents it to the ALU. It takes source 1, presents it to the ALU. And since they're both presented to the ALU, I can say add R5, comma, R2, comma, R3, or I can say add R5, comma, R3, comma, R2. Those are exactly the same. Now the instruction will be different, but since it presents both the data to the ALU, this has a community property, and they'll add the same. Okay, Then it takes the destination and stores it into the destination. Let's look at another one. Let's look at an immediate mode. Okay, here's an immediate mode right here, add and and. So we have a source, so it takes the source and presents it to ALU. It takes the immediate instruction, in the instruction, it's right here, 5 bits. So how large can this be? 1F,
32, 31, 32.
well, think about it.
16.
Close.
An F is
15.
Oh,
How small can it be?
negative
Negative 16. Right? Remember, this is a 2's
Why
complement.
would that be 1F then? Wouldn't that just be F?
One F. That's 5 bits. Right? So if that was all ones, that would be what? If it was 1F, it'd be what? What's the decimal number?
Negative 16.
No.
15. 1F is 15.
No, 1F is not 15. 1F is 32.
What is that?
F is 15.
Negative 1. That's negative 1. 1F is, remember, this is a what?
You're saying 1 and F. I thought you were saying a single F.
No, 1F. 1F, right here, 5 units. This is, does everybody see that, why that's a negative 1?
No.
Add one to.
Okay. Do I need to go over 2's complement arithmetic?
No.
Well, then why can't you see that was negative 1?
Yeah, just take NOT and add 1 and get 1.
Yeah. So that's negative 1. Negative 16 is what? Is that negative 16? And 15 is? Right there. So on an immediate number, it takes this number, remember it's a 2's complement number, so it will sign extend this bit. Because it has to make it as 16 bits to do finite arithmetic, right?
Yeah.
So you can use immediate adds and ands. The thing you have to be careful with is that's all the bigger number you get.
So, I'm just trying to understand what's the difference between immediate then and the register, because immediate comes from somewhere else.
No, immediate, this number is embedded right into the instruction. So I'd say this, I'd say add, my destination, let's say this is R3 and this is R1, add R3, comma, R1, comma, minus 5. So I'm taking R1, adding minus 5 to it and storing it in R3. That's immediate because I have this immediate value. I cannot say R1, comma, 75, right? What kind of error is that? That's called, what kind of error?
Overflow.
No. It won't assemble. There's only one kind of error that you can't assemble or compile. You guys not learn that? That's called a syntax error. It's not logical error. Syntactically, how do I represent 75 in 5 bits? I can't. Therefore, it won't assemble. Right? Remember on assembly errors and compile errors, when you compile, you can compile bad stuff. You just can't compile things that are syntactically incorrect.
Instead of writing 75, could you write a register number?
Yes, that's not immediate though. Oh, excuse me. That's not immediate. That's what? That's register. See right here? So here I can say add R3, R1, R2, and then it can have 75 in R2. Because R2 is 16 bits. Now I can have minus 32K to plus 32K. Okay? Everybody see that? Well, hey, good luck to you guys.